This example demonstrates the operation of a special optimization technique used to design narrow bandpass NBP filters with the additional requirement that their layers have quarter wave or multiple quarter wave optical thicknesses. This requirement allows for a special monitoring approach called turning point optical monitoring. Only thanks to this monitoring approach can one successfully manufacture NBP filters with many dozens and hundreds of layers. In the file, Project Menu of OptiLayer, open the directory LEC25D9. Load into RAM the data files needed to run this exercise. These are the substrate glass N equals 1.52 and the layer materials N equals 2.35 and N equals 1.46. In the synthesis menu, select the filter design mode. It is organized as a 6-step dialog. The first step is to select the layer materials used to design the filter. Most often, NBP filters are two-component multilayers. In our case, two materials are loaded into RAM, and their selection has been already checked. By clicking the Next button, we move on to the second dialog step, where the parameters of the design filter are set. We will design a filter with the following parameters. Filter central wavelength of 600 nanometers, 1.5 nanometers half width at the 89.13% transmittance level, corresponding to an attenuation of 0.5 decibels, 4.5 nanometers half width at the 0.1% transmittance level, corresponding to an attenuation of 30 decibels. Click the Next button to move on to the third dialog step. At this step, the number of spacer layers, the number of filter cavities, is set. The recommendation for this number follows from the theory of Chebyshev filters. Based on the parameters set at the step 2, the required number of spacer layers is estimated at 4. At the next fourth step of the dialog, a filter prototype is selected. The parameters of the filter prototypes are listed in lines M and S of the prototype specification part of the Step 4 window. The M value corresponds to the number of layers of the first left mirror of the prototype, and the S value indicates the order of the spacer layers of the selected prototype. The bottom line corresponds to the initial filter prototype, built using the design approach proposed by Alfred Thelen in 1966. The orders of all spacer layers of this prototype are always equal to 1. It is possible to specify a set of almost equivalent filter prototypes with similar pass bandwidth. This is because there are two ways to control the filter bandwidth, either by changing the number of layers of filter mirrors or by changing the orders of the spacer layers. Increasing the orders of spacer layers while reducing the number of mirrors layers makes it possible to obtain other prototypes with practically equivalent spectral properties. Note that the transmittance of the selected filter prototype is shown on the right side of the window. After one of the filter prototypes has been selected, we move on to the next, fifth dialog step. At this step, it is necessary to optimize the filter parameters. These parameters are the numbers of layers of quarter wave mirrors that make up the filter, and the orders of the filter spacer layers. The optimized parameters are integers, and a special integer optimization procedure is launched when you click the Start button. The results obtained in the course of integer optimization are reflected on the right side of the Step 5 window. Usually, good filter designs are obtained in a short time, and the integer optimization procedure can be interrupted by clicking the Stop button. Note that this is the same button that was in the state Start before the procedure started. If this button is already in the Start state, it means that integer optimization has already completed. Now you can select any of the designs listed on the right side of the window and proceed to the last sixth step of the dialog. Note that the integer optimization was performed under the assumption that the incidence medium has the same refractive index as the substrate. At the last dialog step, the actual refractive index of the incidence medium, usually air, is considered. For this reason, The resulting transmittance shows excellent target compliance, except for in the passband region. It is not a problem to improve the transmittance in the passband region by applying a simple anti-reflection coating at the top of the obtained design by selecting this option. Now the resulting design can be loaded into the general information window in the T and R and phase window by clicking the Finish button. Note that all layers of the final design, except for the last two, have a quarter wave or a multiple of a quarter wave optical thickness. This ensures that turning point optical monitoring can be applied to produce it. Several examples of filter designs are stored in the design database.